Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to discuss past year's exam papers. This is frame analysis using stiffness matrix method. Okay, this is actually past year's exam papers December 2015. Okay, question number 4. So this is the diagram. Okay, this diagram has actually 4 elements. Okay, 4 elements with not 4 elements, has 3 elements and 4 nodes. 3 elements and 4 nodes. So they are node A, B, C and D. Okay, so let's go through the question. Okay, this is a rigid jointed plane frame that is supported and loaded as shown. Analyze the frame using stiffness method. Consider bending effect only. Consider bending effect only. Given that the flexural rigidity EI as 200,000 kN meter square. Okay, question number 1. Okay, for question number 1, establish the element stiffness matrices and the equivalent element nodal force vector in the global coordinate system. Okay, there is the word element here. Element. Establish the element stiffness matrices and the equivalent element nodal force. Means that what we need to establish in the first question are, okay, there are 3 elements, so we have to establish K1, K2, K3, as well as equivalent element nodal forces. Means that we have to establish as well Q1 node for element number 1, Q2 node for element number 2, and Q3 node for element number 3. Okay, so before we start doing this, so what I want to show to all of you here is, okay, frame has actually combination of truss as well as beam. Okay, in real condition, truss got the effect of axial rigidity as well as flexural rigidity. Okay, the flexural rigidity in frame, flexural rigidity, okay, in frame, okay, is EI. Okay, and axial rigidity in frame, okay, is EA. So flexural means bending. Flexural means bending. Flexural means bending. Axial, and another one is axial. Okay, so consider bending effect only means we need to consider EI only, and we can neglect the effect come from axial rigidity. Means that we can assume A is equal to 0. Okay, A is equal to 0. But by having combination of these two, flexural rigidity as well as axial rigidity, what we need to do is, what I mean is, we need to consider, okay, let's look at the formula. Okay, let's open the formula. So this is actually for frame structure. This is for frame structure, and inside the formula, this is the formula, this one. Okay, we have to use the element stiffness matrix, okay, down here. Okay, we cannot use K prime. We cannot use this K prime because this one is for local coordinate system. Okay, what we analyze is actually global system. Okay, this one is global system. Global system. So for global system, we need to refer to the formula as shown here. Okay, and it is K, representing element stiffness matrix, and in frame there are 6 by 6 here. We found that it is 6 by 6. Why it is 6 by 6? Because we have 3 representing near and another 3 representing far. Okay, near 3 are representing near end and another 3 representing far end. So we can see in this diagram. Okay, in this diagram. And in frame, since we have possible horizontal displacement, vertical displacement, and rotational displacement. So we need to consider three displacement possibility. Okay, means that we have 3 degree of freedom per nodes. 3 degree of freedom per node means that we have 3 here in near, okay, near end, and we have another 3 in far end. Okay, so that is why we have 6 by 6. So total for element we have 6 DOF per element. We have 3 per nodes. We have 6 per 6 for element, because element consists of 2 nodes, and one node in frame consists of 3 degree of freedom. And for one element we must have 6 degree of freedom, representing 6 by 6 matrix in the element stiffness matrix. So this is actually the formula. However, okay, let's look at the statement, okay, down below here. When for frame where axial deformation are ignored, okay, axial deformation, okay, EA, it is about A. So axial deformation, when axial deformation are ignored, or we neglect the A value, okay, or we consider bending effect only, so that is the same meaning. So means that A is equal to 0. When A is equal to 0 means that in the equation, in the formula, so all, okay, that have A will be cancelled. Okay, all will be cancelled. All. Okay, actually not much. It is only a few formula representing, I think 4 values only. It is 12 over L cube, and then we have 6 over L square, and then we have 4 over L, and then we have 2 over L. Actually we have only 4 values. Okay, 4 values in this formula. Okay, in this formula, and inside this formula we can see that there are CX and CY. CX and CY, just like what we have done previously under thrust analysis. We need to identify CX and CY. We don't calculate CX and CY in beam. Okay, in beam, but in frame, since the degree of freedom in X, we count back the degree of freedom in X direction and Y direction. That is why we have to determine back the CX and CY. So means that in the diagram we need to identify the coordinate. We need to put the arrow in order to identify or to calculate CX and CY. So we look at back to the question. Okay, this is the question. So by looking at this question, okay, we have four nodes. We have A, B, C, D, or 1, 2, 3, 4, doesn't matter. Okay, we have here A, B, C, and D, and we can label each of this member A. We have member AD. We can label member AD as element number 1. Okay, and then we have member BD. or BC or CD, okay, doesn't matter. This is number 2. Okay, we label one by one. Okay, it's up to us where which one we want to label first, doesn't matter. So this is number 3. So we have 3 element, and then we have to put arrow. We have to put arrow because the arrow is needed in order to calculate Cx and Cy. Because in order to calculate Cx and Cy, we need to know where which is near, which is far, because we have to use this information far and near in order to identify the value. Okay, so we have to put the arrow. Doesn't matter, we can put in any direction that we like. And another thing that is important in order to calculate Cx and Cy is coordinate. So we have to put coordinate. And by having this frame, so I want to choose another origin. I don't want to choose A, B, C or D as origin, because if, for example, if I choose A as origin, C will be negative coordinate, so I don't want to have that. So I will choose another origin. Okay, let's say the origin is 0, 0. So I will do like this. Okay, so we have another coordinate here, and then here. Okay, this one I will put as origin. Okay, this one I will put as origin. So this is 0, 0 coordinate. Okay, then from this origin I will put the coordinate for A, B, C and D. So we have A as 0, 4, 0, 4, and then we have C as 5, 0, and then we have D as 5, 4, and then we have B as 5, 8, 5, 8. Okay, 5, 8. So having this information, we can be able to establish Cx and Cy. Cx and Cy. So we establish Cx and Cy. Okay, so for Cx and Cy for element number 1. For element number 1, Cx is 5. Cx is 5 minus 0 divided by 5. It is equal to 1. So Cx is equal to 1. Cy is equal to 0. Okay, for horizontal member, Cy is equal to 0. And then we have element number 2. For element number 2, we have 5 minus 5. For vertical member, Cx will be 0. Cy, we have 8 minus 4 is 4. Divided by length 4, it is 1. Okay, and then for element number 3, so we have the same value. Cx is equal to 0, Cy is equal to 1. Okay, anyway, the Cx and Cy value, okay, whether it is positive or negative, depending on the arrow. That's why the arrow is very, very important. Okay, so this is the value. So we will actually substitute this value, Cx and Cy, into the formula. Okay, into the formula. Okay, so we can have this matrix. Okay, this matrix by Okay, for example, 12 EI over L cube. So for element number 1, the length is 5. Okay, length is 5, so it is 12 divided by L cube. It is 12 divided by L cube. It is 12 divided by L cube. It is 5 cube. It is 12, again, 12 divided by L cube. Okay, it is 0.096 times CY. Times CY, CY is 0. So the first value is 0. So as usual, we do it one by one. Okay, to calculate K1, K2 and K3. But what most important is the label. Okay, the label. The procedure to establish K1, K2, K3 is actually the same with what we have done previously in beam and frame, except the formula is different and the degree of freedom also different, because frame has 3 degree of freedom per node, so we produce 6 degree of freedom per element. Okay, so what most important is the label. So we will have this K1. Okay, in terms of EI, we don't have EA because A is equal to 0. The value, the axial effect is neglected. So what most important is the label. Okay, the label. So we don't put the label yet, and by looking at the diagram, because A, B and C actually fixed support, so there are 9 DOF for constraint system. So we have 3 DOF in unconstrained system. Okay, unconstrained system. This one representing the 3 degree of freedom in 3 degree of freedom in unconstrained system, representing unknown displacement du, and 9 degree of freedom in constrained system, representing unknown reaction Q unknown. So okay, based on the question, so we will actually establish K1, K2 and K3 as usual using the formula given, and then what most important is the label. So let's label it now. Okay, so we have, okay, at D we have 1, 2, 3, and then at A we have continue with 4, 5, 6, and then continue at B with 6, 7, 8, 9, and continue with 9, 10, 11, 12. 9, 10, 11, 12. Okay, doesn't matter. Based on the question, we don't need to establish the structure stiffness matrix, the capital K, because there's no statement, okay, asking you to establish the structure stiffness matrix. Okay, in question A, you just need to establish element stiffness matrices, K1, K2 and K3, and you don't need to show the 12 by 12 matrix, because we have 4 nodes. 4 nodes means we have 4 times 3, we get 12, right? So the total size of matrix for the structure stiffness matrix is 12. But in the question, there's no statement mentioning about establishing the structure stiffness matrix. It is just establish element stiffness matrices. So we just need to know, and we need to be able to imagine, okay, the 12 by 12 matrix, the position, but not all value. So which values in the structure stiffness matrix that is important, it is actually 3 by 3 matrix only. Okay, 3 by 3 matrix, because we need to determine the unknown displacement considering unconstrained system, because there's no effect of support settlement here. So we just need to focus to the unconstrained system. Means that we need to establish K structure stiffness matrix just up to 3 by 3, 3 position. Okay, 3 position, and we need to establish as well the stiffness equation corresponding to unconstrained degree of freedom. So means that until 3 degree of freedom only. Okay, until 3 degree of freedom only. Okay, so anyway, we need to label first. Okay, label first. So we have element number 1. The label is 4, 5, 6, 1, 2, 3. So this is 4, 5, 6. This is 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. And then we will have K2. Also 6 by 6. And the label is 1, 2, 3. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. So we have 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. Okay, 9. It is 6 by 6 matrix. So we have to calculate all this value and put inside this K1, K2, and K3 in matrix form. But we don't need to calculate or establish the 12 by 12 matrix for structure stiffness matrix. Okay, because there's no question asking you to do that. Okay, you just have to focus on the K up to 3 degree of freedom only. Okay, so for K3, so we have K3. So I will not show all this value. Okay, you will do it by yourself. So I just want to highlight the important things, the difference in frame compared to previous, compared to beam and compared to truss. Okay, so for element number 3, we have okay, from the arrow we know that C is near, so it is 10, 11, 12, 1, 2, 3. 10, 11, 12, 1, 2, 3. So we have 10, 11, 12, 1, 2, 3. 10, 11, 12, 1, 2, 3. Okay, so what we need to have is actually after this, okay, of course we need to have the structure stiffness matrix, but up to 3 degree of freedom only. Okay, so we will later establish K, which is equal to K1 plus K2 plus K3. This is actually for question B. Okay, because for question A, we just need to establish element stiffness matrices K1, K2, and K3, and another three equivalent nodal forces, equivalent element nodal forces for Q1 node, Q2 node, and Q3 node. Okay, this is K. Okay, as usual, K1, K2, K3 we combine to have the structure stiffness matrix, and this frame has 12 by 12 matrix because in total there are 4 joined. 4 times 3 is equivalent to 12, so we have 12 degree of freedom representing 12 by 12 matrix in structure stiffness matrix. However, there's no question asking you to do that, and you need to understand that what most important in order to establish the unknown displacement is actually focusing on the unconstrained system only. Means that in unconstrained system we have 3 degree of freedom, 1, 2, 3. So we will actually establish K, the capital K. Okay, the capital K that we are going to establish is only this 1, 2, 3. 1, 2, 3. So we get the value from K1, K2, and K3. K1, K2, and K3. Okay. We move to the second part of question 1. The second part of question 1 is, okay, the second part of question 1 is this. Okay, we have to establish, okay, the first part is this one. This is the first part. This is the second part. Okay, the second part is equivalent element nodal forces. And we know that in frame, it is just like beam. Okay, this frame has UDL. UDL is member with load with UDL. Means that we need to distribute UDL, because UDL is subjected along the member, and the member cannot carry load. What we need to do is to distribute it equivalently to the nodes. It is Q naught. Distribute it equivalently, we call it as Q naught. Okay, and by looking at the diagram, we will have the value for Q naught for element 1 only, because element number 2 does not has member load. Okay, and element 3 also does not have member load. Only element number 1 has UDL, has member load, member with loading. Okay, so we just need to focus on this. Okay, for Q1 not only, because Q2 not and Q3 not, we already know that the value, all the values inside Q1, Q2 not and Q3 not are 0. Okay, so I put it here. So we have Q. Okay, we have Q1 not. So we want to establish this value. Anyway, Q. Okay, for Q2 not. Okay, 0, 0, 0, 0, 0, 0. Okay, label is equal to K2. Label K2 is 1, 2, 3, 7, 8, 9. It is 1, 2, 3, 7, 8, 9. This is 1, 2, 3, 7, 8, 9. And then we have Q3 not. Okay, there's no value because there's no loading that is subjected on the member. Okay, 0, 0, 0, 0, 0, 0. Okay, and the label will equal to K3. It is 10, 11, 12, 1, 2, 3. 10, 11, 12, 1, 2, 3. It is 10, 11, 12, 1, 2, 3. Anyway, for Q1 node, we have to determine the value. We have to determine the value. Okay, so we refer to the third pages of appendix. Okay, this one we will use this. Okay, the moment is acting in this direction, and W is equal to, W is 50. Okay, anyway, before I forget, don't forget to include this 3EI whenever we calculate K1. Okay, whenever we calculate K1. Okay, okay, back to Q1 node. It is W is, this is W, and length is 5. Okay, WL squared over 12. WL squared over 12 is, okay, WL squared, this W is 50, length is also 5. So WL squared over 12, we have WL squared over 12. We have 104, 104.167, both 104.167, and WL over 2. WL is 125. 125. And of course, by using this formula, this is for beam, but we can apply to frame structure, where we know that the value for horizontal, okay, this value and this value is equivalent to 0. So we have to compare with this. Okay, it is like this, right? Okay, x, y, z, x, y, z. Okay, the label is 1, 2, 3, 4, 5, 6. 4, 5, 6. So what we need to do is we have to compare. Okay. So for 1 and 3, so we label it first. The label is, okay, the label for K1 is 4, 5, 6, 1, 2, 3. This is 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. So we have 4, 5, 6, 1, 2, 3. So we know that 4 and 1 will equal to 0. 4 is 0, 1 is also 0. 5 and 2 are positive. 5 and 2 are positive. It is 1, 2, 5. 1, 2, 5. And we have 6, which is positive, 104.167. And we have 3, which is negative, 167. 104.167. Okay, so this is actually the value. Okay, copy this. Copy this first. Okay, this is actually the values. Okay, this is the value. Okay, so we will produce Q naught, okay, up to 3 degree of freedom. 3 degree of freedom, because we will only concentrate on unconstrained system, because there's no support settlement, so we can focus on unconstrained system only. Okay, we have 1, 2, 3 here. 1, 2, 3. 1, 2, 3. We focus on this. So, okay, from Q1 naught, Q2 naught, and Q3 naught, we have this. This is actually 0, 1, 2, 5, and negative 104.167. So all this we will substitute into the stiffness equation. Okay, the stiffness equation is Q is equal to KD plus Q naught. Remember, we just need to focus to 3 degree of freedom only. Okay, because 3 degree of freedom representing unconstrained system, and in unconstrained system there are unknown displacement. So we will have this equation. Okay, it is 3 by 3. This is d1, d2, d3. d1, d2, d3 plus, okay, Q naught. Okay, for Q, since there's no moment and there's no horizontal load and point load at node number 1 or at unconstrained, okay, at D, not node number 1. Okay, so this is 0, 0, 0. and we have 0, 125 and 1004.167 negative. Okay, so this is 1, 2, 3. And K also we consider up to 1, 2, 3 only. Okay, then having this, we will of course carry this to this side, and we will have this format. So we have three simultaneous equation in matrix form. Okay, it is like this. So just like what we have done previously, after we have reached this step, we will continue to solve this using calculator. Okay, using equation, choose 3 unknown. Okay, so by putting all the values a1 until d3. Okay, we have the x, y and z value representing d1, d2 and d3. And actually, if we refer back to the question, the question asks us to compute the rotation at D. Compute rotation at D means that we need to establish, D, the label is 3, means that we need to calculate D3 only. D3. Of course, we solve D1 and D2 and D3, and by solving the simultaneous equation or the matrix, we will straight away get all these 3 value, but I just want to see what is the answer for D3. Okay, so basically this is how we analyze the analyzed frame. It is combination of thrust in terms of the frame has coordinate. We have to put coordinate, we have to put arrow, because we need to identify or calculate Cx and Cy. Okay, it has this characteristic which we get from thrust. Okay, because the effect of EA in the real frame. Okay, frame has combination of EA and EI. Okay, in real situation. But basically in analysis we ignore the axial deformation because the effect come from axial is very small and can be neglected. That is why the analysis, the complexity of frame analysis will reduce, because we cancel all EA in the formula. So we will calculate only 4 values. Actually repeat, it is a value that is repetitive value. Okay, it is 12 over L cube. It is 6 over L square. It is 4 over L and 2 over L only in the matrix. Of course, in the formula, we need to times with Cx and Cy. Okay, and then we need to understand the question. Okay, whenever the question does ask us to give in full structure stiffness matrix, like what we can have here. Okay, we just need to have up to 3 degree of freedom, because there are 3 degree of freedom in unconstrained system, and in unconstrained system we have unknown displacement. Okay, and by solving simultaneous equation corresponding to unconstrained degree of freedom system, we will get unknown displacement. And if we need to continue to calculate the reaction at the support, we will of course continue using stiffness equation, focus on the position, which position, and we determine the value based on the position, and we will calculate the value using matrix multiplication. Okay, so I just want to discuss up to question B, because this is about the basic thing about frame analysis. The basic thing about frame analysis that students need to understand. Okay, I believe frame is actually after you have gone through beam analysis and frame and truss analysis. Of course, I believe that you will not face problem to understand frame analysis. Okay, what most important, you have to understand that in frame analysis, we have the same procedure like what we have done previously in truss and beam, except the degree of freedom, okay, is different due to the effect, okay, due to the flexural rigidity effect as well as axial rigidity effect in frame. Okay, so I hope you understand about what I have explained in this video. If you have a question, you may ask me later. Okay.